This is Vikas Srivastav again, founder and CTO at AlmaBetter. So I hope you all are having a great time, right? So it's a really good time learning about very technical stuff, right? Which will help us understand the very foundations of data science, right? So we are currently in the statistics module, and in fact the maths module, right? So we have started learning about statistics, right? So you got a bit of idea about summarizing data, right? So some time back we had the class on summarizing data where you're only focused on getting this statistics or the summary about the data which we're observing, right? So and then we understood uh, a lot of concepts in depth about probability theory, right? So we talked about the concept of sets, etc. Then we talked about random variables and different type of distributions, right? We also talked about uh, joint distributions and right. So all of these concepts that we have covered will help us develop our notions coming forth, right? So today we are going to start a very uh, crucial part of statistics, what which is called as inferential statistics, right? So there's one part of statistics that we have covered that is called descriptive statistics, right? So there we're talking about describing uh, describing our data using summary statistics, right? So that's what we have learned earlier, and then we learned a lot about concepts and probability theory, right? So today we're going to talk about inferential statistics. So I just want you guys to take a go at okay, so I'll just share the Padlet link, okay, over the chat. Okay, so if you guys can hop in on the Padlet, right? So I just want you to tell me what do you understand when I say the phrase inferential statistics or statistical inference, right? So I just want you guys to guess, right? Because this is going to be very crucial part of statistics. And in fact, more than 90% of questions in your data science interviews, they're going to come from inferential statistics. So can you guys please tell me your notion of or your understanding of what do you think inferential statistics is about, right? So can you please post your answers? So I want every one of you to get involved in this. This is a really interesting aspects of statistics that we are going to learn, and it's really illuminating in a way, right? So if you think about a lot of processes and phenomena, in fact a lot of business problems, they can be simply solved using statistical modeling, and inferential statistics is going to help us do that, right? So Shweta is saying making generalizations, and then Sumanta is saying drawing conclusions and inferences from a given data. Okay, used to infer about the data, about estimation of parameters, that Shubhal is saying, and Shriram is saying used to infer about the data, make inference. So there is a very interesting answer by Dristanta. Sorry, I lost. Yeah, so make inference about the population from the sample. That's a really smart answer from this Santa. That's great. Uh, what uh, what else, right? So some Surya is saying getting an estimation uh, of output based on few things. Okay, Nikki is saying making conclusions. Uh, all right, so making inferences, of course. When we talk about statistical inference or inferential statistics, so there has to be something which is related to making some inference. But what is the inference that we are going to make about, right? So I think I can also, yeah, scroll down. So Prashant is saying making an estimate from data based on statistical knowledge. Okay, all right. So Rishabh is saying inferencing or conclusions based on data, right? So making inference about the population from the sample, that's what Dristanta had said. And I think that's the most accurate answer I could have gotten, given that you guys are just starting out in terms of learning inferential statistics. Okay, so a great, yeah, well done, guys. So I think, yeah, you are getting to the point of it, right? So inferential statistics or statistical inference is all about understanding or understanding or making inferences about the characteristics or properties of a population by understanding a sample, right? So here there are two important terms, a sample and a population, right? So our first goal is to understand what a sample is, what a population is, and then we'll see how can we make inferences about a population, about the properties or characteristics of a population, just by looking at a sample, and what advantages does it help, right? And where and how does probability theory help us in doing uh, or developing notions about doing such inferences, right? So firstly, let us acquaint ourselves with the notion of a sample. In fact, we'll talk about specifically about a random sample. Okay, so uh, okay, so before we get into the term of a random sample, we need to understand what a population is, right? So again, I'll just want you guys to tell me your notions about what a population is and what a sample should be. Okay, so firstly, let's talk about population. So what do you think a population should be? Okay, so it's still, yeah, so population is complete data. Okay, and the entire data can be called like a universal set. That's what Sudeep is saying. And then Shubhal is answering collection of objects. Uh, okay, so population is in universal. That's what Jayakishan is mentioning, right? And where are the rest of the fellows? So I can see around 29, 30 people, but I cannot see 29 answers or the post here, right? So uh, guys, so this is the time to actually make some guesses about what you're going to study, right? So population, Prashant is saying, consists of all data points. It's like a universal set, right? Okay, so all right, so I'm getting pretty interesting answers. So yes, so most of you are correct that population is essentially a universal set, right? It also, loosely speaking, it can be referred to as the entire data. Let's say we're talking about a specific, let's say, uh, a variable. Okay, so for example, let's say height, right? So, uh, so if you consider all the population, as in all the, if you consider all the events in your sample space, or in the, let's say, you have an exhaustive set of space, so that can be referred to as population, right? So population consists of uh, all the events that can exist, let's say, in a probability space. So that's what a population refers to, and this is again, loosely speaking, refers to the entire data that can be made available to us. uh, so a population in a way is a theoretical concept. So essentially, if I want, if I can ask you guys, so what do you think the theoretical or the size of population should be? So what do you think the theoretical size of a population should be? So you can basically post your answers in the same post. Okay, so what do you think the size of the population, or in fact the theoretical population, right? So it's essentially a theoretical concept, a theoretical notion. So yeah, most of you are saying infinite, right? So exactly. So population sort of corresponds to an infinite collection of data, or infinite. It corresponds to infinite set of events. Okay, or we can say that it's very large, right? So it is very large. So if you start counting all those things which are contained in your population, you will be spending years and millions of years, in fact, counting it, and you will not be over, right? So that's what we mean by population. And I'm really happy that you guys have the notion of population, and that's pretty crucial in understanding what a sample is, right? So a random sample is essentially a set of items selected from a parent population, right? So a random sample is essentially a set of items selected from a parent population, and it has to satisfy two conditions to be called a random sample. Okay, so the first condition is that the probability that any item in the population is which is included in the sample is proportional to its frequency in the parent population. So this is the first criteria for a sample to be called random, as in the probability that any item in the population which is included in the sample or part of the sample is proportional to its frequency in the parent population. So this is the first condition. The second condition is the inclusion or the exclusion of any item in the sample operates independently of the inclusion or exclusion of any other item. So let's say from the parent population, which could be, let's say, uh, uh, a huge collection of, let's say, pencil items. Okay, that could be, let's say, so it could refer to the, let's say, the size of the pencil, right? And we have a population for all the set of pencils that we can find, right? So that can refer to the population. And let's say I select around 100 pencils from that particular population, right? So let's say if I discard any particular pencil based upon my discretion, or include any other pencil instead of something else, so all such selection, they operate independently. Okay, so it does not matter if I select some other, or if I choose any particular pencil, so it does not actually matter. Okay, so the inclusion of any item in the sample, or the criteria for any item to be part of the sample, it essentially operates independently of the inclusion or exclusion of any other such item, right? So these are the two main conditions for a sample to be called a random sample. So essentially what we are doing, we are randomly selecting items from our population, and let's say storing them in a bag, and that we can call that as a random sample, right? So of course the probability that any item in the population which is part of the sample, its frequency will be proportional to so the let's say this probability that any item will be selected or will be part of the sample is essentially proportional to its frequency in the parent population. Let's say my parent population contains pencils of, let's say, different brands, maybe Camlin, Apsara, or anything as such, right? So whatever be the frequency of those items in the parent population, so that the same, so the probability of a particular item in the sample will be essentially proportional to its frequency in the parent population or the original set, right? So these are the two criteria for calling a sample to be random sample, right? So essentially you're randomly selecting without disturbing any behavior or any attribute related to the items or the objects in your sample. Okay, so this is the notion of random sample. So let's move ahead. Okay, so there is some notation that we'll be using in this particular class. So a random sample is made up of independent and identically distributed random variables, and they're denoted by capital X's, right? So you learned about this earlier, right? So we can denote a random variable by a capital X, and a random sample is supposed to be made up of, or it is constituted by independent and identically distributed random variables, which can be denoted by capital X's, right? So there is a shorthand notation to denote a random sample, which is referred by X underline, right? So this is X underline, and this is used to denote a random sample. And because I told you in the beginning that, yeah, random sample is made up of these identically and independent, independent and identically distributed random variables. So your X underline can essentially be, let's say, X1, X2, Xn. So these are all IID random variables, and so they are, let's say, n. Your random sample is constituted of n elements. So this is how we can refer to this particular random sample, which is denoted by X underline, right? So X1, X2. So these are all IID random variables. Okay, and that is what will say that a random sample is said to constitute of. Okay, and then let's say you have an observed sample, or maybe you got a sample by doing some experimentation. So the values or the sample values will be denoted by small x underline, and these will be X1, X2, Xn. All of these X1, so X1 will be the value taken by, let's say, this X1, capital X1. Small x2 will be the value taken by, let's say, this capital X2, and then the small xn will be the value taken by capital Xn, right? So remember that all these xi's, they are essentially random variables, and they are independent and identically distributed, right? So this is important, and you've learned about the concept of IID random variables, right? So this is how we'll denote an observed sample. Okay, this is how we denote the random sample, and by small x underline will denote an observed sample. Okay. So yes, I'll give you an example for these as we move ahead. Okay, so just hang on. So yeah, we'll clarify all this notation. So maybe let's say your random sample could be, let's say, the heights of students in a class. Okay, so that capital X would be the random sample, uh, uh, would be the heights of the students in the class, and the height of each student, it can be said to be, so each student can be said to be drawn from the uh, population of quite larger size, and each of those so heights corresponding to each of those students can be said to be independent and identically distributed random variables, and this small x1, x2, xn will be the heights of those students in the particular class. Okay, so that is how we can you can interpret this, right? So all right, so essentially small x1 is the value which can be taken by this x1, capital X1, right? Small x2 is a value which can be taken by this random variable capital X. Okay, so small x's always correspond to the values, right? And capital X's always correspond to the random variables. Okay, so I'll just write this so that you can get the notion. So let's say you did a survey of students in a class, right? So these students can, of course, come from a larger chunk of population, right? That's why we are referring to them as a random sample of students. Okay, so this is your what we'll say as the random sample. So this is, of course, first the notation, as in we'll specify uh, uh, specify the random sample. So here, let's say x1, x2, and then xn. Okay, so let's say, so this is a random variable, this is again a random variable, right? This is again a random variable, and all these random variables are there essentially independent and identically distributed. Okay, so they all have this very same properties. Okay, so of course to a particular random variable we can associate a probability distribution, and that probability distribution can have certain parameters, right? So these random variables can be associated with let's say a probability distribution, right? So they can, right? And so when we say that they're independent and identically distributed, that means they are characterized by the same similar probability distributions with so where the distribution parameter, let's say theta, so they are all characterized by the same theta. Okay, so these are all distinct random variables. Okay, and then your observed sample will be denoted by small x. In fact, I'll just use a curvy notation so that you understand. So the small x is essentially a small x1, small x2, right? So this small x1 is a value. So let's say for x1, so let's say there was a particular student s1, so this takes a value s1. Okay, and then let's say there is another student which is, let's say, drawn from a population which is characterized with by this random variable x2. So it will take a value x2, right? So in this particular fashion, so xn, let's say there is nth student and xn. Okay, so of course you have understood the concept that a particular random variable can take a lot of different possible values, but here there's an important distinction, as in x1 is a value taken by capital X1, x2 is a value taken by capital X2. Okay, and x1 is a value which this random variable capital X1 can take. Okay, so there could be a lot of different candidate values for which can be taken by capital X1. So I hope you are able to understand the difference between the random sample notation and the observed sample. Is it clear, guys? Sumanta and Smruti. So okay, perfect. So don't think of all of these values taken by a single random variable. Okay, x1 is a value taken by this capital X1 random variable. All of these are different random variables, but they're independent and identically distributed, as in they all have the same underlying probability distribution, which we can say that they are that distribution will be, let's say, of the population. Okay, so because we can assume that a population follows a particular probability distribution. Okay, and we'll see what is the meaning of all this, right? So we have this, let's say, distribution parameter theta. So this could be the characteristic of the population, right? So this could be, so let's say the heights of all the males in India, right? So that can be a population, right? Because it's quite a larger chunk, right? And so when, let's say, the heights of all the males in India, so they follow a normal distribution, right? So in this case, we'll have two theta. So one is of course mu and another is sigma square, right? So mu corresponds to the mean of the population or the average height of the all the Indian males, and then sigma square will correspond to the variance of the heights of all the Indian males, right? So these two parameters are essentially what governs the population, right? So they describe the properties of the population, and all these individual random variables x1, x2, so they are thought of coming from the same underlying probability distribution, and that's why they're called as independent and identically distributed. And small x1, x2, xn, so these are values which can be taken by independently by all of these random variables, which are IID random variables, right? So S1 could be the student which came from the population, S2 could be another student which came from the population, right? So that's what the meaning of the random sample and the observed sample. So observed sample is essentially corresponding to the values of the heights, and capital, so this capital X underline essentially denotes the random variable which corresponds to the heights, and small x's are essentially the values which you can provide, right? So let's say if I took 50 students in the class, so one student could have the height of, let's say, 1.62, another student could have the height of, let's say, 1.58, 1.75. So we can have, let's say, 50 such students, right? So all these values will correspond to this particular small x bar, right? So that means we have observed that these are the heights of the students, right? So that's what the meaning of the random sample and observed sample. Okay, so the population distribution will be specified by a density or probability function denoted by fx theta, right? So you know that a probability density function has a, so of course we have learned about different probability distributions, and we have seen that a particular distribution has an associated distribution parameter with it, right? Which can be generalized with the notation theta. So in the case of, let's say, exponential distribution, this theta was lambda. In the case of normal distribution, this theta would correspond to mu and sigma squared, right? So there we have essentially theta 1 and theta 2. And then let's say in the case of Bernoulli distribution, so we have p, right? So this is what we denote as the population parameter of the distribution, right? So these are the notations that we'll be using ahead in the class. Okay, so let's move ahead. Okay, so yeah, there's one important concept that you already know, that the linear combination of independent random variables, right? So x1, x2, xn, let's say these are n independent random variables. So expectation of some of these individual random variables will essentially be the summation of individual expectations. Okay, so this you have already know, right? And then similarly is the case with variance. So the variance of the sum of the independent random variables is essentially the sum of individual variances. Okay, so that is what we mean by so that is so these are the formulas for representing the expectation of sums of the independent random variables and the correspondingly the variance. Okay, so let's move ahead. So now we come to a very important point right? So of course we have been talking about a lot about statistics, but we haven't actually gave a very precise definition of what a statistic is, right? So statistic is a singular form, and statistics is a plural form, right? So statistic is a function of x underline only, and it does not involve any unknown parameters, right? So essentially a statistics is a statistic is defined as a function of x underline, as in it is a function of your the sample only, or your random sample, right? So for example, a particular statistic could be the sample mean, which is the mean of the sample that you have observed, right? So this will be essentially x bar is equal to 1 by n multiplied by sigma xi, right? So uh, this is what we can call as a valid statistic, right? So here we are only focusing on uh, the values which our x underline can take, right? So this is what we call as the sample mean. So let's say you you are a curious experimenter, and you went ahead and observed the heights of a sample of 50 students, right? So what would be the sample mean? So the average of the height of those students, right? So that is what we mean. Okay, so essentially a sample set is like a parliament. Okay, so essentially, yeah, it's a uh, what should I say? So essentially, a sample is just a chunk, a smaller chunk of the bigger population, right? So in this case, uh, you can define the sample mean, which will be a statistic, because it only is a function of the values taken by uh, these observed this observed random sample, right? So wait a second. Okay, so sample mean is pretty straightforward, as in, let's say you observed a sample of 50 students, and you essentially observed the heights of those 50 students, but of course you can do a lot of other observations, such as, let's say, weights or PMIs or anything as such, right? So in this case, if you're considering that our x small x underline essentially is the heights of different students in our sample, so the sample mean will essentially be divided is essentially be the sum of the height of all the students divided by the number of students in the sample, right? So and this is a function of x underline only, right? Here we do not need any population parameter to calculate or quantify our sample mean. So that is the definition of a statistic. Okay, similarly, if you talk about sample variance, here n is essentially the size of the sample. So size of the single sample that you have observed. So n is the size of the sample. So similarly, sample variance is also denoted as s squared, which is 1 by n minus 1 multiplied by this term, which is xi minus x bar whole square, right? And I'll come to this particular point, why we do not have 1 by n, but why do we have 1 by n minus 1, right? So n minus 1 essentially gives us an unbiased estimate of the sample variance, which I'll cover towards the end of the class. Okay, so because a lot of people who actually study these things for the first time, right? So they get confused, why are we not using n, but you are using n minus 1. So that thing will be covered when we talk about estimation of parameters of the distribution. Okay, so these two things can be called as the statistic. Okay, so now let's say you do not know the population mean, okay, which is denoted by mu. So if you come up with a statistic which is 1 by n multiplied by sigma xi minus mu squared, so this will not be a statistic because mu is not known, right? So if mu is known, this can qualify as a statistic, but let's say some things which are not known, so this will not qualify as a statistic. Okay, so a statistic, as I told you, is a function of x underline only, as in it only we can only define it in relation to the sample that we have observed, right? So this is generally denoted by g x underline, right? So g is a function, and as I told you that a statistic is a function of x underline only. So statistic can be generally denoted by G of X underline, where G simply denotes a function, right? So since because as I can tell you, right? So let's say you have this sample mean, which is, let's say, X bar. Okay, so this is nothing but sum of Xi divided by n, right? So in fact, let's denote this as capital X bar. Okay, so your so statistic is essentially a function of X bar. Okay, so this can also be written as G of X bar. Okay, because it's only using the values which are taken by the random variables in your sample, or the random variables which are constituting your sample, right? So essentially this is what we can also denote with Gx bar. And similarly, let's say we have the sample variance, which is denoted using this. Let's say, so this will be, let's say, Xi minus X bar whole squared. So this will again be uh, can also be, so let's say there is another function G1, or maybe I can use another notation. So let's say H, so H of X underline, right? So these, so whatever statistics that you can come up with, if they are functions of X underline, as in they only need the values of your observed sample, then only they will qualify as a statistic. Okay, so that's the definition of a statistic. And uh, because a statistic is a function of random variables only, right? So it's a function of random variables only, so it will be a random variable itself. Okay, so it will be a random variable itself because it is essentially a function of random variables. So in a way, that you have understood that a random variable is a function which maps an event or an outcome to a particular number, right? Now this particular statistics is again a function on top of these random variables. So in a way you can think of them as a composition of functions which will again be a random variable, right? So let's say uh, this H of X bar can be written as, let's say, H of, let's say, G of maybe all those G of Xi's, right, which are part of your, so X bar is essentially all these Xi's, right, all these Xi's, right? So so here we have this composition that H of G, right? So this is the composition which is essentially can be thought of as a function only, right? So your statistic uh, is essentially a random variable itself. Okay, so this should not be very difficult to grasp, but just keep in mind, because the statistic is a function of random variables, and random variables themselves are functions of, let's say, events which map a particular outcome to a real number. So a statistic is itself a random variable, and because a random variable to a random variable we can associate a probability distribution. So for this statistic we can have a sampling distribution. Okay, so we'll talk about sampling distribution more in a while, but this is the notion of a statistic. So may I know from you guys if you're able to understand what a statistic is? It's pretty straightforward, but I just want to know if you have understood what a statistic is, right? So
So hello,
statistic.
hello Vikas.
Yes.
I'm Sumanta.
Yeah.
So Vikas, so could you give a proper example, like from the past slide, it's a bit confusing, like X1, X2, and X3. What are, can you give a proper example? Like for example, we are taking there are population and we are taking some part of it, and what are these X1 and X2? For example, X1 is random variable of heights, and X2 is the weight. And this way, could you please explain this?
No, so let's say, so you observed a sample where your capital X, so X underline essentially denotes the, let's say, heights of the student. Okay, so let's say X1, as I told you. So just have a look at this particular thing, right? So this is what I mean. Okay, so small x1 is, let's say, the value of the height which is taken by the random variable capital X1. X2, small x2 is the value of the height taken by the random variable capital X2. Okay, so so x1, as I told you, so for a particular student, okay, which is coming from a population. So the x1 random variable, essentially what it does, so the outcome is could be, let's say, that student, okay, and it maps from that student the to the real number, which is the height of that particular student, right? So capital X1 is a random variable, right? And all these x1, x2, xn, these are all random variables, okay, and they are all independent and identically distributed, right? So they all come from the underlying probability distribution, which is what we refer as the population distribution, okay. So that is what I mean by all these capital X1 and small x1. Is that clear?
Yeah, so this is clear, but so x1, so small x1 is the value of capital X1, right? So
Right.
small x2 is the value of capital X2.
Right.
But you wrote it. So for example, I'm taking an example of one person. So small x1 is the value. Suppose capital X1 is the height and capital X2 is the weight.
No,
So
no. So that's where you're confusing yourself. So capital X1 and capital X2, uh, so they will all correspond to the so in your capital X underline. So this will correspond to the, let's say, a random sample of heights of the students in a class. Okay, so that is what I mean. And then only they will be independent and identically distributed, because the height of, let's say, the population, that will be, let's say, the average height of the population could be, let's say, 1.7 meters, and that is where it's coming from, right? So you cannot as of now, you should not assume that x2 could be weight, let's say xn could be, so weight so if you want to define the weight, so the weight of the population could be, let's say, average weight could be let's say 60 kg, right? So there the mu is different, okay. So it will not be independent and identically distributed, because the population parameter or the distribution parameter are different, right? So all these x1, x2, xn, they will correspond to the heights only, okay. So I hope yeah, that should make sense. Okay, so do not get confused. So whenever let's say I'm talking about a sample, so here I'll say that, yeah, these so this is the sample, random sample of the heights of the students in a class, and all these students, they come from a population, right? They all come from a population, and because they come from a population, so population has an underlying distribution defined by a particular parameter, let's say theta. So in the case of normal distribution, that parameter will be mu or sigma squared, and that mu could be, let's say, the average height of the population, okay. So and all these random variables x1, x2, xn, so these are all independent and identically distributed. So I hope that makes sense. So if you're not able to reconcile, so maybe you'll need to just go through this again, and you'll be able to understand. And in fact, let me just get back to your question. In fact, I'll elaborate on it when we actually understand the central limit theorem, right? So this will become more clear, okay? So what I actually mean, right? So when we actually come to understand what a sampling distribution is, so this particular thing will become really clear, okay? So just hang on for a while, okay? So as I told you, that because a statistic is a random variable itself, that so it will of course have a probability distribution, and that is what we'll call as the sampling distribution of this statistic, okay. So okay, so now let's talk about the first statistic that we defined, which is the sample mean. So suppose we have an independent and identically distributed random variables xi, where I can range from, let's say, 1 to till n, each with mean mu and variance sigma squared. So this mean mu and sigma squared, this corresponds to the parameters of the population, okay. So this corresponds to the population of the parameter, right? So Sudeep is asking 1 by n summation xi minus x bar is a statistic, right? So of course, so let's say if that is a function of x underline, so it will be a statistic. So let's say if you were defining, let's say, something like xi minus x bar, where x bar essentially is the average, let's say, height of the sample, okay. So wherever we are only using the observed values of the sample, so whatever function that we can come up with, so that can be a valid statistic, okay. So it should be only a function of the observed sample, or a random sample. Okay, so that is what I mean. So so okay, so so all these x1 x2 till xn, so these are all independent, so these are all random variables, right? So not, so you should not confuse that capital X1 capital X2, so these are different random variables with different parameters, right? So you, as you're saying, that x1 could be the height, x2 could be the weight, but in that case the let's say if you're saying that which correspond to the height corresponds to the weight, but here they come from the same underlying population. Okay, and the population distribution is characterized by your single mu and sigma square. Okay, so so here all the xi's could correspond to, let's say, the height, or xi's could correspond to, let's say, the weight. Okay, so the sample mean, as you have seen, the definition is simply the mean of the sample. Okay, so the mean, let's say, for example, the mean height of the students in that sample. Okay, so one important thing is the expected value of the sample mean. The expected value of the sample mean will be the population mean mu. Okay, so there are a few things which you need to be aware of, right? So population has, let's say, it is defined by a probability distribution. Okay, so it is defined by a probability distribution, and in this case, let's say this so if you calculate the mean and the variance, so it, let's say, it's defined by mu and sigma square. Okay, so I'm not, of course, necessarily talking about the normal distribution, but of course, for any distribution you can define the uh, mean and the variance, right? That's what we have learned. So let's say this population probability distribution is characterized by these parameters, right? So so here's a very interesting thing, right? So you have a sample mean, which is, let's say, 50 students or 100 students, right? So you can calculate the uh, sample mean, which is average height of the students in the class. So you'll come up with some value, right? So this is a pretty important statement, which says that the expected value of the sample mean will be the population mean only. Okay, so this is a pretty important, because uh, you only have looked at a particular sample and you're saying that the expected value of the sample mean will be mu. Okay, so the expected value of this sample mean, which is a statistic, right, which is essentially a random variable. So think of x bar as a random variable only. So the expected value of this random variable is nothing but the population mean. Okay, so you don't have to worry about how are we getting this, but you can think of it in this way, that essentially, because that sample is coming from the population, so the average height of the students in that particular sample would be pretty much similar to the average height of all the students in, let's say, India. Okay, so that's what this is telling, right? So the expected value of the random variable x bar, okay, is essentially mu, which is the population mean. So there's another interesting property, that the variance of this random variable, which is capital X bar, this is sigma square by n. Okay, so the variance of this random variable x bar. Okay, so x bar is a random variable, and because for a random variable we can associate a probability distribution. Okay, and once we have, let's say, the probability distribution, we can find the expected value, the variance, or maybe higher moments, right? So the variance of this sample statistic, which is the sample mean, will be sigma squared by n. Okay, so this will be sigma squared by n. Right. So yeah, so mu is the population mean and x bar is the sample mean, right? So you need to understand this, right? So mu and sigma squared, they give you the characteristics, or they define the properties of the population as a whole, but the X bar only tells you about the sample, right? So X bar only gives you the idea about the sample, and the goal of inferential statistics is to use the information that we have about the sample to estimate or infer properties of the entire population, which is, let's say, mu. So let's say you are not uh, uh, the mu and sigma squared is not known, because think of this in a very standard way, right? So let's say you are an experimenter, you want to find the average height of all Indian males. Okay, so you want to do this, but because of lack of resources, you cannot go and individually observe each of those people at the same time, because of course their height can be uh, they can be growing, right? So at the same time you cannot or maybe let's say within a fixed amount of time you cannot survey the entire population, right? So there you have the constraint in for resources. So what we can do at best is that we can look at, let's say, 1,000 Indian males. Okay, let's say we can look at 1,000 Indian males, because that is doable. We can survey these 1,000 people, and whatever the statistic that we can come up with, we can say that our population or the population mean can be inferred from the mean of the sample that we have observed. Okay, so because you cannot survey the entire population, because that's highly impractical. Okay, so that's highly impractical. So if you want to make inferences about the population, so let's say if someone asked you, tell me what is the average height of Indian males. Okay, so what is the best that you can do? So the best that you can do is you can survey, let's say, 1,000 people or 10,000 people, and you can calculate their average heights, right, of all these 1,000 or 10,000 people, and you can say that the uh, population height or the population mean will be the average height which we have gotten from the sample. Okay, so that is what I mean. So expected value of X bar will be population mean if n is very large, right? Exactly. Yeah. So it will be, but yeah. So okay. So just think of X bar as the random variable only, right? So for a random variable, you can find the expected value. So expected value of X bar will be mu. Okay, and the variance of X bar will be sigma squared by n, and similarly you can define the standard deviation of X bar as sigma by root n. Okay, so so now let's talk about a very important result in all of statistics, in fact, which stems from the probability theory. So this is what we call as the central limit theorem, and this is arguably the most important result in all of statistics and probability theory, right? So I'll talk about what central limit theorem is. Okay, so okay, so let's see. So let's say I'm all so. I want to find the sampling distribution. So how do I do that? So let's say this is a sample which I can call as sample S1. Okay, so this sample, so all of the samples which I'll consider, let's say they consist of 100 students. Okay, so let's say sample consists of 100 students, and here in the sample I am observing their heights, right? So so there are 100 students, and in this sample I'm observing their heights, right? So these are, let's say, 100 students, and here what we can do, we can find, let's say, the sample mean. So let's say x1 bar will be, let's say, 1.665. Okay, so this is what we get. Okay, now let's take another sample of another 100 students. Okay, so let's say this is the sample of, let's say, another 100 students, right? This is the second sample, and for this, let's say this will be the average height could be, let's say, 1.68. Okay, so similarly I can have a lot of other samples of different 100 students. Okay, and so let's say for this we'll get something else, right? So maybe, let's say, 1.70. Okay, so what you, if you find the sampling distribution, as in, let's say you draw the histogram. Okay, so here, let's say on the x-axis you have different buckets of height, so maybe 1.5 to, let's say, 1.6, or in fact we can make it quite small, so 1.5 to 1.58, and this could be 1.58 to 1.61, and this could be, let's say, 1.61 to 1.64, something like this. So we are making different buckets, so 1.64 to, let's say, 1.67, and this could be, let's say, 1.67 to 1.7, and here similarly we can have 1.7 to 1.73, right, 1.73 to, let's say, 1.76, something like this. So we can go on. So now you observed, let's say, n different samples. Okay, so you observed n different samples, and what you are trying to do, you are trying to basically find the distribution of the sample means. You're trying to find the distribution of the sample means. So let's say x1 lied in this particular interval, which was this, and there were, let's say, 10 of them. Okay, so I can have, let's say, this corresponds to the count of them, right, which is the frequency. So we are essentially creating the histogram, right? And let's say x2 was maybe, let's say, 15 of them, right? So we can have, let's say, 15 of them here, and then let's say this was around let's say, because this is the average height of all, so average height lies around this, so maybe, let's say, we had around 25 of them, right, out of the n samples that we have explored. Okay, so here we could have something like this. Okay, so something like this. Okay, so what does central limit theorem tells us? Okay, so central limit theorem tells us, let's say, whatever be the underlying population distribution. So that underlying population distribution can be, let's say, a binomial distribution, a Bernoulli, exponential, Poisson, anything as such. It can be any distribution. Now what you do, you find the sampling distribution, as in the distribution of the sample means, right? So earlier we were talking about a single sample, but let's say if we had different samples of the same sample sizes, right? So we have the same sample size for all these n samples. So now if you look at the sampling distribution of the sample means, so that will by central limit theorem, it is guaranteed that the sampling distribution will be a normal distribution. Okay, this is the main result of central limit theorem, or the main proposition of the central limit theorem, is that whatever be the underlying distribution of a population, it could be any population probability distribution, right? It can be a Poisson process, it can be, let's say, Bernoulli, exponential, Poisson, anything as such, right? So now what you do, you calculated, let's say, the sample means for all the other samples, right? And let's say each of these samples had capital N is equal to 100, which is the individual sample size. And now you have n different samples, so you find the sampling distribution, as in you find the histogram for that, so that will give you a normal distribution. So this is a pretty important result, and this is what we refer to as central limit theorem, right? So even if it's a non-standard distribution, right, so the underlying distribution could be anything, but your sampling distribution will always be a normal distribution, right? So that is really important. Okay, so let's look at the visualization, and this point will become really clear, right? So here let's pick any particular probability distribution which has two parameters, let's say alpha and beta. Okay, so let's pick a particular okay, so how actually are we creating the histograms? Okay, this is a nice question. So let's say there could be 10 different samples whose average height comes out to be 1.65, and that is what will be denoted by this particular histogram. So this value is 10 here, right? So there could be 10 different samples whose average height comes out to be 1.65. There could be, let's say, 25 different samples whose average height comes out to be 1.70. So that is how we are getting the frequency histogram. Okay, so this small n could be, let's say, 1000. Let's say small n is 1000. That means we surveyed 1000 samples of 100 students each. Okay, so that is what I mean. Okay, so we surveyed 1000 samples where each sample was 100 students each. Okay, so there could be 10 samples for which the average height was 1.65. There could be 25 such samples whose average height was 1.7, right? So if you create the frequency or you can create the histogram, so this will follow a normal distribution. So I was just getting to this particular point only. So let's see. So here we have a particular probability distribution which is governed by alpha and beta, right? So if I change alpha and beta, so our probability distribution will change, right? So similarly, we can tweak around with beta, and that will give us. So let's say I have alpha as this, right? So let's say alpha is this and beta is this. Okay, so maybe I can make this to 4. Right, so it's pretty close to 4. Okay, so now, so the central limit theorem tells you the theoretical distribution should be. So let's say I increase the sample sizes, right? So let's consider each of the samples. Each of the samples have 15 elements in it. Okay, so the sample size, as in the size of individual sample, is 15. That is really important to understand. The individual size or of each sample is 15. Okay. Okay, so alpha and beta are essentially some parameters of a probability distribution. So for the case of, let's say, a binomial distribution, it could refer to the n and the p's. Okay, for, let's say, for any other distribution, it could refer to their parameters. So here we have, so this is any distribution for which there are two different distribution parameters. Okay, so this refers to any general distribution in a way. Okay, so I hope that clears your answer. Okay, Smriti. Okay, so now here's a very important thing. So now let's begin our experiment, and what we'll do that. So how many draws we want to make? So let's say we want to make only one draw. Okay, so and each draw will have 15 elements. So let's just have a look, and you will be able to see, right? So 15 different values were picked, right, from a single sample, right? So here one value was from here. So let's say in the case of heights, so there was one height maybe 1.56, there was another height 1.6 from a single sample only, because the draws refer to a single sample. Okay, so one draw refers to a single sample only, and where the sample size is 15. Okay, so now let's sample a lot many times. Okay, so let's do such samples a lot, right? So if we if we repeat this experiment a large number of time, okay, so here I'll do, I'll just reload this, and I forgot to mention one important point. Okay, so let's say our alpha is something like this, our beta is something like this. Okay, right? And so sample size is, let's say, we are keeping as 15, and we are only we are only drawing one sample at a time. Okay, and so whatever you are seeing in the count here, so it's essentially the average. Okay, so whatever the points, as in 15 points we got, right? So the average of those 15 points was calculated, and it came to be somewhere here, right? So it came to be somewhere here, right? So this corresponds to the let's say mean height of this particular sample, which is 1, the sample 1. Now we can repeat this experiment again, right? So we can draw another sample of 15 elements each, right? So now the average height will, let's say, it corresponds to this particular point, right? So this corresponds to this particular point, and this could be, let's say, x2 bar, which is the average height of the second sample that we drew, right? Now what we can do, we can draw such samples, right? So a large many times, right? So we can perform this experiment. So here, of course, we are drawing only one sample at a time, right? So if you repeat this experiment, let's say, a large enough times, okay, so if you repeat this experiment large enough times, so this will eventually so this particular distribution of the sample means it will follow a normal distribution. So that is what we mean by that is what is given or guaranteed by the central limit theorem, right? So let's increase the value of draws. Okay, so at once we'll be, let's say, drawing 10 samples at a time. Okay, so let's increase this because we, or maybe let's say let's draw 50 samples one at a time. So all of these samples will individually have 15 elements in those, and in single experiment here we are randomly drawing 50 different samples where each of those samples have 15 elements, right? So first of all, I want to know from you guys if you're able to understand what is sample size and what is the number of draws. If you are able to understand, then only we can understand central limit theorem here. So can you please let me know if you understand what sample size is? Sample size is essentially the number of elements within a single sample. Okay, and the draws is essentially the number of different random samples that we'll be drawing once at a time. Okay, so okay, Rajat is saying that he doesn't understand what a draw is. Okay, so see, let's go back to this particular example. So here, let's say if you draw S1, S3, S1, S2, S3, S4, S5, right? So, or let's say till S30. So there will be 30 different samples. If you draw them one at a time, so that will be, let's say 30 draws. Okay, so that's what I mean. Okay, so that's what I mean. So, okay, so let's perform this experiment and you will be able to appreciate what this is. Okay, so of course this is only one sample at a time, and let's say I'll draw 50 different samples, each with sample size 15. Okay, so see, as you can see, there were 15 such draws. Okay, I'll repeat this experiment again. Okay, so now we are again drawing 50 samples, right? So so as you can see, the distribution of the sample means, okay, the distribution of the sample means, okay, that follows a normal distribution if we perform this experiment large number of times. Okay, so this is what is given by the central limit theorem. Okay, so one important question I want you guys to tell me, right? So this is of course corresponds to the mode, right? So this is the mode, and this will be, let's say, the median, and here we'll be having the mean. So this is where we'll be having the mean of the population. Okay, this is where we'll be having the this particular point. In fact, I'll just clear this out, and yeah, just hang on. So maybe, yeah, okay, I'll use something else. Okay, so this sorry, I don't know what happened. Okay, so let's keep beta to be something this, and then it was something like this, right? And we're doing a lot of so our sample size was, let's say, 15, and we're doing 50 draws. Okay, of course they will happen one after another, as you were seeing. So in one draw, what is happening? So in one draw, whatever the points we got, its average was calculated, and this average came out to be this particular point, right? And if we talk about from the population perspective, so of course this is the underlying distribution of the population, and this corresponds, so this is, let's say, the mode, okay, because that's the most frequent one. And here we'll have some median, and here, let's say, we'll have the mean. Okay, here we'll have the mean. So so the theoretical distribution of the sample means will look something like this. Okay, so if you do this experiment large number of times, so let's do this, let's keep doing this. Okay, so for each draw of for each draw of a sample, what is happening, that 15 points are we are randomly sampling 15 points from the population that is constituting our sample, while calculating the average of that sample, and that is what is being plotted here, right? So let's, right, and if we do this experiment large number of times, so this is essentially the distribution of the sample means, right? So if you understand this particular concept, you will be able to understand what central limit theorem is, right? So this is essentially the distribution of sample means. Okay, right? So for a single draw, you're getting one value of the sample mean. For another draw, you're getting some different value of the sample mean. You're doing a large number of draws, so for each draw, you're getting different sample mean. And if you plot the histogram, or if you find the probability or distribution of all these sample means that you have got for each such draws, so this particular distribution will be a normal distribution. Okay, so I can do this experiment large number of times, and you can see that eventually what will happen, that the distribution of the sample mean will approach a normal distribution. This is the main result of the central limit theorem, right? So I can change my alpha, so that will of course correspond to some different let's say something like this, right? So here, let's keep doing this particular experiment. Okay, so this is of course a different distribution, as you can see, because I changed the parameters, let's say alpha and beta. But still, if we keep repeating this experiment, so whatever, regardless of the underlying population distribution, right? So this refers to the underlying population distribution, right? So regardless of the underlying population distribution, the distribution of the sample means will follow a normal distribution. Okay, so let's change alpha to something different, right? I'll change beta to something like this, and I'll again, yeah, keep doing this particular experiment. So this particular curve is the theoretical result, which is essentially given by the normal distribution, right? And if we keep doing this experiment again and again, so we'll see that the sample means actually follow a normal distribution. Okay, so Sudeep is asking a question that if the n is very small, will it follow a normal distribution? So for very small n, it will not follow a normal distribution. Usually it's said that for central limit theorem to hold, the sample size, as in the number of elements in each individual sample, it should be greater than 30. That is what is usually said for central limit theorem to hold. But for some distributions, it's not even required to be greater than 30. For some underlying distributions, if we're taking the sample size, let's say 20, then also CLT can hold. But it's usually recommended that yeah, the sample size should be greater than 30, and there will more often than not will be guaranteed that the sample means will be normally distributed. Okay, so it's essentially a thumb rule, but it holds for most of the occasions. Okay, so if your sample size is quite large, okay, so it is essentially, and if you have let's say a lot of different such samples, all the distribution of those sample means they will follow a normal distribution. So this is what is meant by the central limit theorem. Okay, so you can experiment with different values of alpha, different beta, right? So let's do some experiment where we only take one sample size, right? So as you can see, so when my sample size was 15, so this was the theoretical, right? So this particular curve is the theoretical distribution, right? So if let's say sample size is 1, so it's not essentially a normal distribution in this case. But if I increase the sample size, so it will sort of it will ensure that the sample means will follow a normal distribution. Okay, so let's say if I do this particular experiment, and if I keep, yeah, right, so this will not follow a normal distribution because our sample size is really small. That is only we are drawing one, we are only having one element in individual samples. Okay, so if each sample has a larger number of elements, as in the sample size is large, then more often than not central limit theorem will hold. Okay, so you can perform this experiment, and I encourage you guys to perform this experiment on your own and see how are we getting this distribution of sample means which essentially for large number of such experiments will follow a normal distribution, right? So this is what the central limit theorem tells us, right? So central limit theorem states that the sample mean of a sufficiently large number of independent and identically distributed random variables is approximately normally distributed. So the larger the sample, the better the approximation, right? So it's essentially it's approximately a normal distribution. It's not exactly a normal distribution, because a normal distribution in that case, of course, corresponds to a theoretical distribution. But if you have large number of samples and if you keep repeating the experiments, then it will approximate to a true normal distribution. Okay, so this is what's the idea of the central limit theorem, right? And whatever be your underlying population distribution, if we are drawing a sample from that population, which can follow any probability distribution for that matter, right? So if you're drawing samples from that particular population, you're calculating the let's say sample means for all those samples, and so these sample means will follow the normal distribution given large sample size. Okay, so this is what I mean by central limit theorem. So are you guys able to comprehend what what central limit theorem is? Can you please let me know, right? So here we are talking about distribution of sample means. Okay, so for each sample you can calculate a sample mean. Then you can have a lot of different such samples, and you can have sample means for all those such samples. And if you find the distribution of all these sample means, so given enough sample size, it will follow a normal distribution. And this is the main result of the central limit theorem. Okay, so all right, so okay, so one important thing is uh, okay, so the expected value of x bar will be mu. Okay, so the expected value of the so your population mean can be inferred from your let's say the can be inferred from your samples only, right? So that is what's the utility of doing inferential statistics, because there we have a lot of constraint on practical resources. We cannot perform experiments or do surveys or obtain observations for the entire set of population. So what do we do instead? We survey a sample from it. Okay, and by looking at the statistics of that particular sample, we can infer the population characteristics or the population parameters, right? So this is essentially where central limit theorem will hold. Okay, so let me tell you one more thing. Okay, so going forward, what we'll have as in you will be asked a lot of questions that, let's say, you observed only one single sample, right? You observed one single sample, maybe let's say of 100 students. So can you tell me what will be the average height of the population? Okay, so there will be using the concept of the or the idea of the central limit theorem, right? Because central limit theorem tells us the sample means will be normally distributed, right? So so whatever population, whatever sample that we are surveying, from that only we can apply the central limit theorem and say that yeah, your population mean will be, let's say, equal to the expected value of your expected value of your sample mean, right? So here, that's the result I'm talking about, right? So because we, by central limit theorem, we are given that x bar will essentially follow a normal distribution with mean mu and the variance sigma square by n, where n is the sample size. Okay, so by central limit theorem we are given this particular result. So we can say that yeah, the expected value of x bar will be mu, right? And the variance of x bar will be sigma squared by n, or equivalently standard deviation will be sigma by root n, right? So we'll utilize these results when we actually do hypothesis testing, right? So that's a really interesting topic, and we'll talk about hypothesis testing day after tomorrow. Okay, so as of now you need to understand what central. So central limit theorem opens a lot of different possibilities for us, right? So we, regardless of whatever the population distribution could be, right? So we are given that let's say the sample mean will be normally distributed with, let's say, mean mu and the variance sigma squared by n, and that is how we can, let's say, infer mu and sigma squared. Okay, so because we can of course survey our samples, right? That is what we are doing in our surveys or experiments, right? So the utility of central limit theorem will become even more clear and pronounced when we talk about hypothesis testing, because eventually there will be using this important concept. But I wanted you guys to know about this important theorem because this forms the base of inferential statistics. Okay, so and this is where probability theory is sort of tied with statistics. Okay, because I don't want to survey, let's say, 100 different samples. Not even I want to do surveys of 10 different samples. I only want to do one survey where I'll let's say have a sample of 100 students, and based on that I want to make some inferences about the population, and I will be able to make that inference only if central limit theorem allows me to, right? So central limit theorem tells me that, yeah, expected value of a sample mean will be the population parameter, right? So a population mean, in fact, right? So but just by looking at a particular sample and incorporating CLT into that, so we'll be able to tell that, yeah, this should be the population mean, right? So there, of course, we'll talk about the confidence with which we can say that, yeah, this should be the population mean, right? So of course those concepts will come in hypothesis testing, but for now you just need to understand what central limit theorem is. Okay, so if I were to say in a particular statement, because this can be often asked in interviews, so you can say that uh, 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 regardless of the underlying probability distribution of the population, if we draw different samples with large enough sample size, so the distribution of the sample means will follow a normal distribution. So that you can say, right, in one line. But so, but however, we need mean and variance of original distribution to get the expected mean and variance of our. See, you're getting confused, Smruti, right? So, see, when you talk about the sample, you know the means of it, right? You know the mean and the variance of that particular sample, right? So the whole idea is we want to use that information to estimate information about the population, right? So what you have told is the other way around, right? So it's not like, if see, then you're defeating the whole purpose of doing the inferential statistics. Here we we are doing inferential statistics only because we cannot survey the entire population. We can only survey a sample, right? And one, so by surveying a particular sample, we'll get the mean of that particular sample, will, let's say, get the variance of that sample, and by using that information we'll be able to infer that, yeah, this should be our population mean, it should be our population variance. So I'll come to the point, how can we get the uh, uh, let's say population mean from the expected from the sample mean? How can we get, let's say, the population variance from, let's say, the statistics observed from our sample? Okay, so does that make sense, Shruti? So it's the other way around, right? Because then you're defeating the whole purpose of doing statistics, because here what we want to do, we only want to look at a particular sample, and based on the statistics of that sample, we want to make inferences about the entire population. Okay, so what are the inferences you are making about the population? That means you are trying to understand what the population distribution is. So you'll try to estimate or infer the parameters of the underlying population distribution just by looking at a particular sample. Okay, so just keep this particular thing in mind. If you are able to understand this, then only you will be able to understand the entire purpose or objective of doing inferential statistics. So I'll just repeat again. So the goal of inferential statistics is to look at a sample, uh, observe its statistics, and then on the basis of that we want to make inferences about, or we want to estimate the parameters of the underlying population distribution. Okay, that's what we want to do, right? So I want to survey 100 people, I want to observe their heights, and whatever information that I'm getting from that, I'll be able to tell that, yeah, the average height of all Indian males should be that. Okay, it might not be exactly that, but that gives us an estimation of the original population mean. Okay, that's why we say that we want to estimate or infer, right? Nothing is of course so precise and approximate, but will be able to tell with certain confidence that, yeah, this our population mean should be this, and I can say this with this much confidence. Okay, so is this particular aspect clear? I just want to know from you guys, because it seems that some of you are confused. So I just want to know from you if you are able to understand whatever we have discussed till now. Okay, we'll of course come to the point where we'll actually make the inferences, right? So as of now, we have just discussed the central limit theorem. We'll talked about the distribution of sample means, etc. Right? Okay, perfect. All right. So, so central limit theorem helps us to do a lot of normal approximations, right? So, let's say you have a, let's say the underlying population distribution is binomially distributed with the parameters n and p, then the sample means will be normally distributed, or let's say the whatever test statistic you come up with, so it will be normally distributed if NP is greater than 5. So based on this, right? So similarly, the underlying population distribution could be, let's say, Poisson could come from a Poisson process, right? So that can again be approximated by a normal distribution, right? So this distribution, when we're talking about normal approximations, so we're talking about the distribution of the sample means. Okay, so yeah, and then we have chi-squared, etc. Right? So okay, so okay, so all right, so let's move ahead. So another statistic that we have is the same sample variance, right? So let's say you again have n independent and identically distributed random variables xi's, and they all come from the underlying distribution mu and variance sigma square, right? So sample variance is defined by this, right? 1 by n minus 1 multiplied by sigma xi minus x bar whole square. Okay, so here also we can say that what should be the expected value of the sample variance, right? So the expected value of the sample variance will be the population mean, which is mu. Okay, and this will essentially be the so in this case, so expected value of x bar will essentially be the mean of the sample that we are observing, right? Okay, so and then of course you can talk about the expected value of the sample variance, because here sample variance is just another statistic, which is just another random variable, and if you have any random variable, you can tell that, yeah, this should be the expected value of that random variable. You can calculate the variance of a particular random variable as well, right? So do not get confused between, let's say, variance of the sample variance, right? So something like this actually exists, right? So variance of sample variance, because your sample variance is nothing but just a random variable, and you can find the variance of a random variable, right? So remember, we have talked about the variance of a random variable, and here we say that, yeah, the variance of a random variable is nothing but the expected value, right? So this is what our, right? So we know this particular formula, right? So for the variance, so where x is just a random variable, right? So here in this case as well, s square is nothing but a random variable only, and we can have a notion that, yeah, expected value of s squared or variance of s squared, right, In fact, we can talk about higher moments, let's say. So uh, uh, right, so we can talk about higher moments of the random variable s squared, which is the sample variance. Okay, so this is what is it. And here, contrary to in this case, the uh, variance, so this SD, which is standard deviation, this is also called a standard error, okay, which is sigma by root n. And in this case, this can be uh, this can be inferred by, let's say, sigma by root, so it's equal to sigma by root n, right? And this is these are the characteristics of the underlying population distribution, right? So it's not necessarily normal, it could be anything, but for those we can of course define the mean and the variance, right? So do not only think about normal distribution here when I say mean, mu, and variance sigma square, right? So are you able to understand that this mean, mu, and variance sigma squared could also correspond to some other distribution, like let's say exponential, right? So can you please let me know over the chat? So you don't have to confuse yourself that yeah, mu and sigma squared is they are let's say reserved for normal distribution, right? So can I get a yes from you guys if you're able to understand that mu and sigma squared, they can uh, uh, correspond to, let's say, any underlying population distribution. Okay. So in the case of sample mean, so when our test statistic is sample mean, so the standard error of sample mean is sigma by root n. Okay, but in this case, let's say we are given this variance sigma squared, so we cannot actually say what will be the variance of s squared. So okay, so here we cannot actually say that what will be the variance of this particular statistic or the random or this random variable, right? So this will be dependent on population distribution. So whatever be the population distribution, variance of s squared will be dependent on that. Okay, so this is pretty important. And one just a specific corollary of it, that the sampling distribution of s squared, okay, when sampling from a normal population, right? So here, if we generally talk about variance of s squared, right? So here it will of course be dependent on population distribution, but let's say the underlying distribution was normally distributed, or was normal. So the sampling distribution of s squared when sampling from a normal population with mean, mu, and sigma squared is n minus 1 s squared by sigma squared. So this particular statistic will be a chi-squared statistic. Okay, so you know what is a chi-squared statistic. So I told you earlier. So let's say you you have z1, z2, right, zn, right, and all of these zis, they are standard normal, they're standard normally distributed, right? So your chi-squared will be essentially the sum of all these standard normally distributed z's. Okay, so this is how chi-squared is defined, right? So because this sum of the squares of your, let's say, all the random variables will be a random variable only. So chi-squared is a random variable. Okay, and and it is this particular random variable is said to have n degrees of freedom. Okay, which essentially corresponds to these different n random variables. In fact, standard normally distributed random variables. Okay, so this is how chi-squared statistic is defined, right? So this is the chi-squared statistic. Okay, so we are talking about the specific statistic, which is the sample variance. So if you calculate this, this particular statistic, which is n minus 1 s squared by sigma squared, right? So this will essentially follow a chi-squared distribution with n minus 1 degrees of freedom, right? So this will be a chi-squared. So this statistic, so this is a statistic which will follow a chi-squared distribution, right? So here, right? So this is a particular test statistic. Okay, this is what we call as a statistic, right? So this will follow a chi-square distribution with n minus 1 degrees of freedom. No, chi-square is a different distribution. Okay, so in fact, what I can do, if you guys are interested, right? So I wanted to actually discuss about chi-squared and all those things when we actually talk about hypothesis testing. Okay, so here what you can do, you can go to functions, you can go to distributions, and here you can. So there's t distribution here. There's no chi-squared distribution, but if I show you, let's say the chi-squared distribution graph, right? So let's talk about the images, right? So if you look at this particular image, right? So this particular image, right? So K refers to the degree of freedom. So for 1 degree of freedom, this distribution will follow this particular curve, right? So this is for 1 degree of freedom. This is how it will look like. But 2 degrees of freedom, it will look like something like the green curve. And then for 3 degrees of freedom, it will look like this, right? So as you can see, this is not similar to the normal distribution. Okay, so does that answer your question? Okay. And similarly, if you can see for the t distribution as well. So if I show you, so t distribution um, follows this. But so for t distribution as well, we have the concept of degree of freedom, and based on the degree of freedom, it follows different density functions. Okay, so they all, of course, are said to be t distributed, but it is dependent upon the degree of freedom as well. Okay, so I'll just come back to that particular point, right? So here what we understood, that sample variance is a statistic which is simply called a random variable, and for this random variable we can tell that, yeah, expected value of this random variable is this, variance of this random variable will be dependent on population distribution, and but if the underlying population distribution is normal in nature, then this particular statistic will be said to follow a chi-square distribution. Okay, so of course, as of now, I'm just quoting the result. We can derive this, but this is not required. Okay, and we want to only highlight those things which are necessary from data science perspective, right? So nobody will ask you that, yeah, tell me why this particular statistic is chi-square distributed. Okay, but you can make these assumptions, let's say in interviews, and they're not going to ask you these questions, right? So let's not bother us as much. They will mostly be asking about, let's say, most of the concepts in hypothesis testing. They can ask you what central limit theorem is, how the central limit theorem helps in doing hypothesis testing. They will ask you about confidence intervals, which are essentially will be covered in the next few classes. Okay, so these concepts you do not have to worry about it. You can just take this for granted that, yeah, this particular this statistic, which can be written as, let's say, n minus 1 s squared by sigma squared, right? So s squared is the sample variance, sigma squared is the population variance. So this will follow a chi-square distribution, right? And for a fixed degree of freedom, we know what will be the probability density function for that particular chi-distributed random variable, right? And we can find those probabilities, right? So these things will, so if we talk about, let's say, chi-squared 10, so that particular value will be able to get, right, from some tables, right? We can also get this from the Python packages only that we have discussed earlier, right? So using the CDF or stuff like that. Okay. So then again we have the T result. So here in the T result, so what happens that in most of the practical situations, you would not have much idea about the population variance, right? So here for this, we assume that, yeah, this particular statistic will be chi-square distributed with n minus 1 degrees of freedom. But here we assume that, yeah, sigma squared is known, right? But in the we'll be using the T distribution where we do not actually know what sigma square is. Okay, so in this case, this Z result cannot be used, which is essentially the CLT. right? This is also referred to as the Z result. So in this case, uh, we'll use the T result in such cases. So this particular statistic, which is X bar minus mu. So mu is population mean, which let's say assumed to be known, divided by S by root n. So S is your sample variance, or uh, S is your sample standard deviation. Okay. So so by using the sample information about the sample standard deviation, the sample mean and the population mean, will be able to approximate this with a t distributed random variable with n minus 1 degrees of freedom. And I don't so I'll tell you the exact definition of t distributed random variable tomorrow. Okay. I don't want to tell a lot of things in this particular class, so I want to keep it a bit light. So I'll tell you about what t distribution is, or t distributed random variable is, in the next class, right? But uh, I can tell you, so t distributed is closely related to uh, your chi-square distribution and a normal distribution, right? So if you look at the wiki page, right? So here, um, so one second, right? So let's not bother about it for now. Tomorrow I'll give you the precise definition of it. So it is uh, it comprises of your chi-square distributed random variable and a standard normally distributed random variable. Okay, so that we'll discuss tomorrow, so don't worry about it. Just keep in mind that t distribution is symmetrical about 0, right? So here we looked at, right? So not the Hotling's t distribution. In fact, we want to talk about student's t distribution. So it's not t square, it's student t distribution. Okay. So this student t distribution, the important things that you should know, that this is this is symmetrical about 0. So this is one important property of the t distribution. So this is how the student t distribution looks like. And if I were to tell you the definition, right? So here, so uh, yeah, let's not bother about it. So it's a bit complicated, so you guys will just get confused today. Okay, so let's keep it for tomorrow's class. But just keep in mind that this t distribution for different degrees of freedom, even for different degrees of freedom, it will be symmetrical about 0. As you can see, it's just only the nature of the distribution is changing based on the degrees of freedom. Okay. And this result is valid only for samples from normal distribution. Okay. So let's say your sample is drawn from a normal distribution, then only this particular result will hold. Okay, as in this particular statistic can be assumed to be t distributed with n minus 1 degrees of freedom, right? And as you know, t distribution is symmetrical about 0. Okay, so this is the result. And the f result is, again, I'll talk about the f distribution tomorrow. But let's say if you have independent random samples of size n1 and n2, and they are taken from normal populations with different variances, let's say sigma 1 squared and sigma 2 squared. So these different samples are taken from different populations with different variances. So here f so this particular statistic, which is s1 squared, that is the sample variance of this first sample. S2 squared is the sample variance of the second sample. And of course, you are, let's say in this case, you know about sigma square and sigma 2 square. So the ratio of these two will be f distributed with n1 minus 1 comma n2 minus 1 degrees of freedom. So I'll talk about the f distribution in detail tomorrow, so you do not need to actually bother about this, and these will never be asked in your interviews, right? So you do not have to fill your head with a lot of formulas and stuff. But just keep in mind, whenever we want to, let's say, compare statistics, or we want to compare sample variances, so there we'll use the f result, as in this particular statistic. So this will be f distributed in nature. Okay, and this is again valid for samples which are only drawn from normal distribution. Okay, so f result relies on samples being drawn from normal distribution. T result also relies on samples being drawn from the underlying normal distribution. Okay, And in the case of uh, so here also for the chi-squared statistic, we are relying on the sampling being done from an underlying normal distribution. Okay, so all these distributions, chi-squared, t-squared, t distribution, or the f distribution, so they all stem from the normal distribution, right? They're not normal distributions by themselves, but they utilize the so they require the random variables which are part of let's say t statistic or your chi-squared statistic. So there we need the concept of normal distribution, just like for this example where we talked about chi-squared statistics. So all these zi's, they are essentially standard normally distributed, right? So this is not exactly following the normal distribution, but this distribution is what we call as chi-square distribution, and this random variable is essentially the squared sum of um, all these independent and identically distributed standard normal random variables. Okay, so of course we'll be discussing them in detail in the coming classes when we actually talk about confidence intervals and hypothesis testing. So for now, just think of these distribution, t distribution, or chi-square distribution. They stem from normal distributions, but they're not normal distributions by themselves. Okay, so that's an important point. Okay, so so now we come to a very important aspect of inferential statistics, that is point estimation. So now what we want to do, so here by looking at the sample, right? By looking at the sample, we want to estimate a particular value of the population parameter, right? So this is what we refer as the point estimation. So for a particular from a particular sample, right? So let's say we get the sample mean, we get the, let's say, sample variance, etc. That we can calculate because we of course have surveyed the sample, so we have those values with us, right? And from this particular sample mean and sample variances, what we can do, we can try to estimate the population parameters. And here when we talk about estimation, we'll be estimating a particular value of the estimation parameter. Of course, we'll talk about tomorrow that we can not only do a point estimation, but we can do a range estimation, as in we can say that the population mean value, let's say, should lie in this particular interval, right? So today in point estimation, we're going to talk about those population parameter estimates which will be point in nature, as in we'll be talking about single value estimates. Okay, tomorrow we'll be talking about estimates which are essentially intervals. Okay, so that's for tomorrow. So let's talk about point estimation. So I have a nice visualization here. So one of the main goals of statistics is to estimate unknown parameters, right? So because you want to understand how what's the characteristics or what's the underlying distribution of the population, right? And because of lack of resources, you cannot survey the entire population. So the best you can do, what you can have a look at the sample and try to infer population parameters from there. Okay, so I hope you guys know what a population parameter is, right? Because I've mentioned this a lot many times. So I just before I move, I just want to get this confirmed from you. Are you able to understand what a population parameter is? As in the parameter which defines the underlying probability distribution of the population, right? So can I get a yes if you know what a population parameter is, right? So in the case of, let's say, population which is normally distributed, right? So your population parameters could be mu and sigma square, which are essentially coincident with the mean and the sample and the variance. Okay, so great. So now here there is a very nice analogy where we can try to understand how point estimation works. Okay, so to approximate these parameters, we choose an estimator, which is simply any function of randomly sampled observation. Just like as we saw that gx underline, right? So that was again a function, right? So here also this is what it means. To approximate these parameters, we choose an estimator, which is simply any function of randomly sampled values or observations. Okay, so here what we have, so you know, so let's say if someone were to ask you, can you tell me a quick way to estimate the values of pi? Okay, so you know that the area of a circle is pi r squared. You know the area of a square is 4r squared. So let's say here uh, this is r, okay, which is the radius of this circle, and uh, so here the side of the square will be 2r. So area of the square will be, so area of square will be 2r whole squared, which is 4r squared, and area of circle will be pi r squared. Okay, and because pi is less than 4, so you know that, yeah, the area of circle is less than the area of the square in this case, right? So now what we want to do in this case, we want to estimate the value of pi. Okay, so we want to estimate the value of pi, right? So pi is simply, if we divide these two, so pi will be simply 4 times uh, s of circle, that is the area of the circle, divided by the area of the square. Okay, so how do we actually estimate this particular ratio, right? So here so from this particular formula, which you know, right? So from this particular formula, pi is essentially 4 times the area of the circle divided by area of the square. So now this particular ratio, which is the ratio of area of circle to area of square, right? So how can we estimate this ratio? By doing some sampling. So what we can do, we can randomly generate points within the square, and what we'll do, we'll count the number of points in the circle divided by the number of points inside the square. Okay, and that will help us give the estimate of the uh, ratio of these areas. Okay, so what we'll do, so let's drop 100 samples. Okay, so let's drop 100 samples. So there are 82 points when we randomly so what your aim is, essentially, let's say you have a square cardboard and you have a circle on it, and what you do, you randomly throw a dart there, right? So you randomly keep throwing dart without the intention to hit the dart in the bullseye, right? That means you're not doing it randomly, you're doing it in a very biased way, right? So let's say you have a square cardboard and there is a circle made as well, and you're just randomly throwing dart without even looking at it, right? So let's say all the darts are hitting these cardboard. So some darts will actually lie inside the circle, but some darts will fall outside of the circle, but of course within the square. Okay, so let's say I do such 100 throws. So in that case, let's say I get 82 such throws within the circle, but total 100 throws, of course, within the square. Okay, so if you use this particular ratio, that is 82 by 100 multiplied by 4, so this gives me the estimate of pi to be 3.28, right? Which is not that far from 3.14, which is the actual value of pi. And just 2 days back, we had the pi day, if you guys actually noticed, right? That's 14th March is called as the pi day. Okay, so now let's drop 1,000 samples. Okay, so let's drop 1,000 such throws on our square cardboard. And what we'll do, we'll count the number of points which lie inside the circle, right, divided by the number of points which are within the square, right? So in this case, so 874 points were within the circle out of 1,100 points, right? Because we already dropped 100 samples earlier, and then we dropped 1,000 samples, so total there were 1,100. Okay, so let's do this again. So let's drop 1,000 samples again. Okay, so let's weight this to be 2,200, 2,100, right? So now the estimate of pi is 3.18, right? Which is pretty close to 3.14, right? So you can keep doing this particular experiment as many times as you want. Okay, so you keep drawing such doing such throws. Okay, and as you can see, so for a large number of throws, by calculating the ratio of the number of points within the circle divided by the number of points within the square, we're able to come up with the estimate of pi, which is pretty close, right? 3.14. Of course, 99 is not there, but it's pretty close, right? So in this way, we can do the estimation of pi, right? So this is just an example, and here what we are doing, we're doing a point estimate. Okay, so this is just an analogy of what we're going to study in the point estimate, okay, or in point estimation, right? So are you guys able to understand what this experiment is and how are we able to get the estimate the value of pi, right? So but here the value is already known. I'm not sure what you're talking about, Sheets. So see, what we consider an experiment. Let's say you are in lockdown and you're pretty bored. Okay, you know from the theoretical result that pi is essentially 4 times the area of circle by area of square, right? But in this approximation, we are not actually using the area of circle and the area of the square. If we did that, then we'll get the actual value of the pi, right? Because that's how the areas of circle and the squares are defined. But in this case, what we want to do, uh, we want to estimate this particular ratio, right? We don't want to use the formula for square and the circle, because that will again defeat the whole purpose of doing this. To estimate this area, what we can do instead, I'll say that let's create a cardboard, okay, square cardboard in fact, okay, and I'll also mark a circle within it, okay. And now what I'll do, I'll keep throwing diets at the square cardboard randomly. So let's say if I did, let's say 10,000 such throws. So what I'll do, I'll count the number of throws which fell inside the circle divided by the total number of throws I did. Okay, and that will give me an idea of the ratio of the area of circle divided by area of square. Okay, so this is what I mean when, let's say, I want to estimate the value of pi, right? So this is a pretty good experiment, right? So here we have almost filled the circle, and if you do keep doing this experiment, you will be filling the circles totally, right? And there will be getting a more approximate value. Of course, that depends upon how much we are doing. So of course, there could be some deviation, right? But it's actually pretty close to pi, right? So this is how we can estimate pi, but just by doing an experiment, right? Right, exactly. So we cannot estimate two parameters at the same time. I did not get your question, Sudeep. Okay, so can you be more discreet? Sheets is saying that here we know that something close to 3.14 is a good estimation. Right, exactly. So of course, in this case, we know that 3.1, whatever we are getting from this particular estimation, that is pretty close to 3.14. The same thing can also be extrapolated when we talk about statistics, right? So let's say if I observe, let's say a sample of 1,000 people, I observe their characteristic, okay, maybe let's say I calculate their average heights, and on the basis of that, I can actually make an inference about the average height of the entire population, and I'll not be very accurate, but I'll be very close to the actual value, right? I might be a bit far from the actual value if I had the capacity to survey the entire population, but it will not be very far from that, right? Well, if your sample is random, right? If your sample is not biased, then only this will be guaranteed. But let's say if your sample is biased, as in let's say you only surveyed those people from a particular demographic region where usually people are shorter, okay? So there, of course, it will not hold, right? So your sample has to be unbiased or random, right? Okay, so yeah, like suppose for a cylinder height and radius r. Okay, so we cannot estimate two parameters at the same time. In fact, we can do those things, right? So we can, let's say, um, we can we should be able to approximate, let's say, multiple parameters of the distribution. So that should be possible, right? So that's possible. Yeah. So because let's say there would be some cases in which we can try to make an assessment. Let's say if our population is normally distributed, only we are given this, but we do not know the parameters of that distribution. But by looking at the sample, we can actually try to make an estimate of the population mean and the population variance. So those things we can try to do, right? Which are essentially two parameters in this case, right? So this is so this example is just to give an intuition how point estimation works. So today's lecture will just be extended slightly, so please do not mind that. I just need yeah, 10-15 more minutes. Okay, so I'll just, yeah, okay. So there is one important method of moments, so that we can get actually the uh, population parameters using the sample parameters. Okay, so you know about the method of moments which I had discussed earlier. So e to the power tx, and this so e to the power tx, I told you that this is a moment generating function, and the expectation of e to the power tx actually helps us give all the order of moments, right? So you know that our exponential see, it can be expanded in this particular fashion: 1 factorial plus tx whole squared by 2 factorial, something like this, right? Tx n by n factorial, something like this, right? So if you take the expectation of 1, so that will be 1 plus expectation of tx, right? So t time expectation of x, right? By 1 factorial, then it will be, let's say, t squared expectation of x squared, something like this, by 2 factorial, right? So this refers to the first order moment, as I've told you earlier, right? First order moment. This is the second order moment. So the method of moments tells us that what we can do, we can equate population moments, that is the means, variances, etc. of the theoretical model, to corresponding sample moments, that is the means, variances, etc. of the sample data which we have observed and surveyed, right? And we can solve with the parameters there, right? So uh, so in this, let's take an example, and this will become pretty clear, right? So let's say we have a random sample from a exponential distribution, and what we want to do, we want to estimate what should be the lambda. Okay, so in our random sample, we have 6 observations. So 14.84, 0.19, 11.75, 1.18, 2.44, 0.53, etc. Right? So these are the 6 points which we have from our random sample. And we are given that this sample is drawn from an underlying exponential distribution with the parameter lambda, and we do not know lambda, and our task is to actually determine what should be the most accurate estimate of the lambda. Okay, so we want to use the method of moments estimate for lambda. So what we'll do, we'll calculate the sample mean. So x bar will be this particular value, which is 5.155. And you know, so here what we are trying to do, we are trying to equate the population moment, right? So for the mean, we'll equate the expectation of x with the mean of the uh, exponential distribution, which is given by 1 by lambda, right? Remember from the exponential distribution class, so the mean of exponential distribution is given by 1 by lambda. So we'll simply equate this to 1 by lambda, and in this case, e of x is nothing but x bar, which is our sample mean, right? So expected value of x is nothing but x bar, and we'll equate this to 1 by lambda, and this is how we can estimate the value of lambda from this particular random sample. So this is just an example, and this is how the method of moments work. And similarly, we can do this for, let's say, you know, the variance for um, uh, the exponential distribution, and you can equate the second order moment for those, right? So of course we'll not discuss that as of now, but this is how method of moments actually work, right? So we'll not worry much about method of moments, which I just wanted to tell you that there's such a method which exists, but this is actually not that popular method which is used. There's another popular method which I actually want to discuss in detail, that is the method of maximum likelihood. So Smoothie is saying, but mean of sample is not the mean of original distribution. So how can we equate? So here what we are doing, that we are not, so here we're trying to estimate the value of lambda. This particular value, let's say if my random sample increases to, let's say, 100 points, okay, so for that I can get different value of lambda, but based on whatever sample I have observed, I am trying to estimate that this could be the possible value of lambda, and that's why I'm equating this, because this is defined, this is on the basis of method of moments, right? So the first moment is expectation of x, which is essentially from our random sample, that will be the mean of that sample, right? And that we can equate that to the, let's say, the ideal mean of the exponential distribution, which is 1 by lambda. And in this case, whatever lambda will get, it will just be an estimate of the actual lambda, and this could be far off from the actual lambda as well, right? So you need to appreciate this particular fact. So let's say if I increase the random sample, or if I do any other sample, so this lambda could be different, a bit different, right? So that is what I do. So see, this is the point of doing point estimate, right? So here, when we talk about point estimation, we are trying to come up with a particular value of the estimate of the original population parameter. Okay, that is the meaning of point estimation. Point estimation is where, so here I'm not saying that lambda should belong to this particular interval, right? So here I'm not saying that lambda, let's say, should belong to this particular interval where, let's say, was 0.09, but in fact I'm saying that lambda is equal to this particular value whatever I have observed. So what is that value for in this case? So let's say this is 0.19, right? 0.19. So this is referred to as point estimation, as in where we are estimating a single value for the estimate of the population parameter. Okay, so lambda is a population parameter. We don't know what the value of lambda is, but this is the best that we can come up with by looking at the sample that we have observed. Okay, so I hope that makes sense. Okay, perfect. So let's move ahead. So method of moments is used, but it's not a very popular method. But I want to actually discuss about method of maximum likelihood, and we'll cover this again in logistic regression as well. So you need to understand this concept a bit as well. So the method of maximum likelihood is widely regarded as the best general method of finding estimators. And here also we're trying to do the point estimates, as in a single value estimate of the population parameter, right? So what do you think the likelihood of a sample x1 comma x2 comma xn? So this constitutes a particular sample from a population with density, or let's say probability function fx theta, right, where theta is the population parameter. Okay, so this likelihood will be given by this particular thing, right? Why should that be? So here we're saying that likelihood of what is the likelihood of a sample? So the likelihood of the sample would be simply, let's say, x1 theta multiplied by x2 theta, right, and xn theta, right? So this is the likelihood of the sample, and this can be written as f of x I comma theta, where I ranges from 1 to n, because there are n components of your sample. Okay, so there are n components of a sample, right? So this is a single sample, remember. So this is what we define as the likelihood of the sample, as in what is the probability of each of those points to be observed. Okay, so we'll multiply each of these probabilities, and that will give us the likelihood of the sample. Now what we want to do, we'll calculate the log likelihood, as in we'll apply the log transformation here, and we'll try to differentiate the log likelihood with respect to the parameters. So for example theta, and we'll set the derivative to 0, which will give us the maximum likelihood estimated. Okay, which will give us the maximum likelihood, and the value of the theta for which we are getting the maximum likelihood, that will be our maximum likelihood estimated. Okay, so let's do an example, and this will become really clear. Okay, so let's say we draw a random sample of size n, that is x1 till xn, from the exponential distribution with density fx is equal to lambda e to the power minus lambda x, right? So this is what we are given. So I'll just use another frame. So let's say your sample consists of these values x1 x2 till xn, right? And they come from the exponential distribution, which is fx, defined as fx comma lambda, in fact, so lambda e to the power minus lambda ex, right? So this is what we are given. And so how do we go about finding the best estimate for lambda, right? So how do we actually go about it? right? So firstly, what we'll do, we'll calculate the likelihood L lambda. So this will be given by product of lambda e to the power minus x I for all I to n, right? So this is what we'll get, right? Xi essentially correspond to x1, x2 till xn. Okay, so there are n components of your random sample, and so let's apply the log transformation here. Okay, so let's apply the log transformation. So we can do apply the log transformation here. So lambda e to the power minus lambda xi. Okay, so of course let's keep this to be log L. Okay, let's not write log L lambda because it's a function of lambda only, right? Now you know about log, important property of log, right? So let's say I have a lot of elements log a b c d, so we can write log a plus log b plus log c plus log d, right? So this is what we can write. So let's use that particular result from the logarithms if you are familiar. So we can write something like lambda e to the power minus lambda x1, sorry, x1. In fact, this will be the log of this, right? So log of lambda e to the power minus lambda x2. In fact, yeah, so something like this. Okay, so this is what we'll have, and so what we can do, so log, so again we'll apply log lambda plus, we can write log of e to the power minus lambda 1 lambda x1 plus, again we'll have lambda plus log of in fact log lambda, okay, plus log of e to the power minus x2, right? Similarly we have this, right? So last term will be, right? So as you can see, there are n log lambdas term, right? So I can combine them together and I can write them as n into log lambda. Okay, and can you tell me what this value will be? So this value will be nothing but minus lambda x1. Okay, similarly we have a lot of other terms x2, right, till minus lambda xn, right? So are you guys able to follow this as of now? Can you please let me know? Okay, so this is what we have, and let's move to the new frame. Okay, so there we'll have log L, which is L is the likelihood of observing that sample, right? So you should be able to understand why I wrote L as the form which I have written here, right? So understand that particular bit, and that's really important. Okay, so now what we have, that log lambda is nothing but n log log L is equal to n log lambda minus lambda times x1 plus till xn. Okay, this is what we have from the last time, right? So this is what we have, so we can take minus lambda common and then we can add all of them together, right? So, and this is what we can refer as n lambda, let's say x bar, okay, which is the x bar will be the sample mean. Okay, x bar is the sample mean. Okay, now what we want to do, we'll differentiate this with respect to lambda, and whatever lambda that we get will be our the estimate for the population parameter, right? So let's differentiate. So d log L d lambda, so this will equate this to 0. Okay, this is what we want to do, right? Because we want to find the that value of lambda for which our log likelihood is maximized. Okay, so you know this from the calculus classes, right? So if you are given a function, you need to find the maxima of that function for which x that function is taking a maximum value. So you differentiate that function with respect to x, and you find out a particular value of x, which gives you the maximum value of the function for that particular x, right? So here also we'll do the same thing. So what will be the derivative of n log lambda? Okay, and then we have d lambda of n lambda x bar. Okay, so this will be 0. So this will be of course n by 1 by lambda, and this will be n n and lambda lambda, so this will be x bar only, right? So this is 0. So now lambda will be simply, so n when n will get cancelled, and lambda will be 1 by x bar. Okay, so this is the same value which we got from the method of moments, right? So here also this is 1 by lambda, right? So so this is the estimate which will maximize the likelihood of observing that sample if that sample were uh, drawn from a underlying exponential distribution. Of course, we can do this for a lot other distribution, but just wanted to take an example of an exponential distribution and so show you that the maximum likelihood estimate of the population parameter, which is lambda, it is 1 by x bar, which is x bar is the population, right? And here this is not actually lambda, this is lambda hat. So lambda hat is actually the population parameter estimate, and of course lambda is your actual population parameter, right? So there is a difference between the estimate and the actual value, right? So estimate uh, is uh, is trying to approximate the value of the actual lambda. Okay, so are you guys with me at this point of time? So this is another way of getting the uh, estimate of the population parameter, which is lambda, and that is and to estimate that, we just need the population mean, and lambda is essentially the inverse of the population mean. Will Emily and method of movements give the same estimate? So I need to actually check on this, but on most occasions they will give you the same estimate, but they might differ a bit at times. Okay, so I'll need to check on this because I have not actually explored method of moments in details because that is not widely used. But most of the time we use the method of log likelihood. But I think most of the times it will give you the same estimate, as in this particular case as well, right? And so there is important properties of estimator. So let us take a random sample x underline, which is this, which comes from a distribution with an unknown parameter theta, and g x underline is an estimator of theta, right? So bias is defined as expectation of g of x underline minus theta. So this will give you the unbiased estimated, right? So when we talked about this particular sample variance formula, right? So sorry. So this particular formula, so if you have 1 by n, then your bias will come out to be non-zero, right? If you have n here, but if you have n minus 1, so the bias will come out to be 0. So that's why this particular sample variance is called as an unbiased estimator of sigma squared. So in this case, s squared is an unbiased estimate of sigma squared, where we're taking n minus 1 instead of n. And I think you guys should try to actually prove this, why this particular n minus 1 gives you an unbiased estimator. So essentially what you need to do, you need to calculate this particular bit. So expectation of s square, which is the sample variance, minus sigma square. So you need to find out this for both, let's say n and n minus 1 cases, right? And see for which you are getting 0 or non-zero. Okay, so this is a very interesting exercise, and you can actually prove yourself that this s square, where we have 1 by n minus 1, that gives us an unbiased estimator of sigma squared, which is the population variance. Okay, so and because this difference is 0, so that's why most of the time we can estimate our population variance with our sample variance. Okay, so that's what we can do, right? And the mean squared error is of course defined by expectation of gx underline minus theta whole squared, right? So you square this term, and this will be expanded as bias squared plus variance. And this is a very interesting topic because this will be covered in machine learning when we actually talk about bias variance trade-off. right? So this will be discussed later on, but for now, just wanted to list down the properties of estimators. An estimator with a low MSE is said to be more efficient. That makes sense, right? So the estimators for which the difference between, let's say, the actual population parameter and your estimated population parameter, if the difference is really low, then that will call as the lower, that will call as the more efficient estimator, right? And and of course, you can ask this question that, of course, we don't know sigma square. That's why we're trying to do the estimate. So how will we calculate this? But uh, this is from theoretical perspective only, right? So let's say if you're doing some theoretical simulations and you assume that your underlying population distribution is, let's say, normally distributed or anything as such, so you can actually calculate this. So maybe what you can do, you can verify this for, let's say, a normal distribution, and see if this actually gives you the unbiased estimate. Okay, so this is what was there in this class. We've talked about sampling, right? So the idea of random sample, we talked about central limit theorem in detail, and then we talked about estimating population parameters, right? So and we also looked at few of these statistics such as sample mean, sample variance, and there are other statistics such as, let's say, this particular statistic which follows the t distribution, this particular statistic which follows the f distribution. So we'll in fact talk about t distribution, f distribution, and the chi-square distribution in the coming classes only, right? So because we'll be doing most of those things, so just stay tuned and you'll get all these concepts clear, right? And you guys don't have to worry that if you're not able to understand in one go, because inferential statistics is actually a difficult subject, and it has tricked a lot of people uh, when so whenever people started studying statistics or start studying statistics, so they often get confused because uh, uh, they're not actually made clear of what is being tried to do, right? So you need to understand what is the overall objective of inferential statistics, and that is how you'll be able to appreciate whatever the techniques that we have, right? So today we talked about point estimation of the population parameters. Tomorrow we'll talk about interval estimates of the population parameters, right? And there we'll introduce you to the notion of confidence intervals, and that is for tomorrow, right? So I hope you guys were able to understand at least 70% of the stuff. If not so, just go through the lecture once again, spend a lot of time with doing the experiments, and maybe, so I have also attached two books in the dashboard. If that's not accessible, so I can add that again, and you can go through those references if you want to read more about it, right? But here, the key takeaways is you need to understand what is sampling, you need to understand what is central limit theorem, what is the implication of central limit theorem. That will of course become very obvious in the coming classes. And then you need to understand the difference between point and interval estimates. And then of course you need to understand how does method of maximum likelihood is done. Yes, I'll add the books, and I have really interesting books which I have been following all along. So there is one book by Hines and Montgomery, and there's another book by Sheldon M. Ross. So I'll add these books, and you can go through them. So just a word of caution: so don't go through everything in the book. Okay, only consult the topics which have been taught in the class. Okay, so just please make sure. Of course, you can do that, but you don't have to know everything, right? We only want to focus on those things which are essentially relevant from data science perspective, and mostly from data science interviews perspective, right? So of course statistics is a really huge subject, and we can discuss a lot of intricacies, but not everything is required to be understood, right? So at times we need to accept that we have certain limitations. We can only cover only certain things or limited things in particular time. So just do that, and you should be fine. Okay, so just follow what we have been suggesting, and just consult these topics from the books that we'll share. Okay, so I'll add the books by tonight, and maybe I'll share the books yeah, just by tonight only. Okay, so don't worry about it. Okay, so let's go ahead and take the quiz. Okay, so can you please log into Kahoot?